Okay, here we are. This is AP Physics C E&M check-in number 10 on capacitors. What this picture is, hopefully you can see it, is you have two parallel plate capacitors. So two plates that'll probably have opposite charge on them. They have a length and a width that are the same, given as 40 centimeters length, width 80 centimeters, and they're 2 centimeters apart. First question asks, in what ways could I achieve an increase of capacitance by a factor of 4? Well, probably remember that the capacitance is equal to epsilon naught A over D, where A is going to be the length times the width. So if you wanted to increase the capacitance by a factor of 4, we could, number one, increase both the length and the width by 2. That'll give us 2, and 2 gives us 4. Or we can cut the distance by a factor of 4. If we get them from 2 centimeters to a half a centimeter, let's say, that would also achieve a capacitance of 4 times as much. Okay, so this would be length times width times epsilon naught, the permittivity of free space, constant. Okay, so that's that question. It says here in the next one, go ahead and calculate with that equation what do you actually get if you put in your numbers. So let's take a look at that. The capacitance being epsilon naught A over D. Epsilon naught is 8.85 times 10 to the negative 12. That's in coulombs squared per Newton meters squared. And then the A in this case is going to be 40 centimeters, which is 0.4 meters, times 80 centimeters, 0.8 meters. And then we're going to divide by the distance between them, which was 2 centimeters or 0.02 meters. It's a really small number for the capacitance. If you do that, you get 1.42 times 10 to the negative 10. Go ahead and try that and see if you get that as a number. But that is somewhere like 14 nanofarads of capacitance. Nano is negative 9. Okay, so we're on to the next question. If, in this case, you put a dielectric material between those plates with a dielectric constant we call kappa equal to 3.5, so you put a material in between. We probably said on one of the other videos or in class that if you do that, you decrease the electric field and the voltage. Charge stays the same. The ratio of charge to voltage gives you capacitance. But if you want to know what is the new capacitance, the way that works is it's just that factor kappa times whatever the original capacitance was. So pretty simply, it's just going to be 3.5 multiplied by what we just got, which was 1.42 times 10 to the negative 10 farads, and that gives you right around 5 times 10 to the negative 10 farads of capacitance. That will be the new capacitance on that capacitor, just by putting that piece of dielectric insulating material in between the plates. Okay, so that was that question. We move on to the next one. This one's a little more using calculus and doing some derivations. It asks us to take this cylindrical capacitor, so it has an inside with a charge of plus Q on it, and an outer part of the capacitor that has a charge of minus Q. Plus Q is at a radius of A, minus Q is at a radius of B, and define the overall capacitance of that capacitor. So first, if you want to do that, I think we probably want to look back and derive what the electric field strength using Gauss's law is for this case. You've got an E dot dA equals the charge enclosed over epsilon naught. Well, you remember back in the day when we talked about a linear charge density. The linear charge density lambda was the charge over the length of that. So we would probably say this is lambda times L over epsilon naught for this particular capacitor. A charge density lambda times the length, where that length would be the length of the wire, or in this case, the cylindrical capacitor. Where do we go from there? Well, we have to use Gauss's law to figure that out. And so you'd have a Gaussian surface somewhere in between the two out at a radius of r. And you would use Gauss's law to predict what the electric field in that region out to r was. And so using the same ideas that we've used so far, the electric field strength and the dAs should all be in the same direction or parallel to one another. So you drop the dot product, the electric field will be outward. It will be uniform on every spot on that Gaussian surface. So that will come out of the integral. And then if you add up all of the dAs, that was just going to be the area of your Gaussian surface, which is a Gaussian cylinder of radius r, so it would be just 2 pi r times the length. That would be your Gaussian surface as a cylinder. So in the end, it would be E times 2 pi r L equals lambda L over epsilon naught. The L's cancel, and a familiar result for a wire or cylinder is you should get the magnetic field, or excuse me, the electric field strength should be equal to lambda over 2 pi epsilon naught r. No L in that region because the L's have canceled out. So that's just the electric field strength. That gets us part of the way there, because we're going to have to figure out what is the potential difference. So the voltage or the potential difference should be E, the integral of E dot dr, and we have to now figure that out from a radius of A to a radius of B, whereas we have the electric field now as lambda over 2 pi epsilon naught r dr from those same limits from r equals A to r equals B. Okay, and so if we pull out those things that are constant, lambda, 2 pi, epsilon naught, that's all our constants, and then we integrate from r equals A to r equals B, you get dr over r, which, if you remember correctly, is just the natural log. So this is lambda over 2 pi epsilon naught log of r evaluated from r equals A to r equals B. At the end, it's going to be lambda over 2 pi epsilon naught r, or excuse me, the log of r. So that's going to be just the log of B minus the log of A, which is the same as the log of B over the log of A. The ratio of log of B over A. The capacitance is defined to be the charge over the potential difference. So I guess there's one other step would be to go back and say, well, lambda is in fact Q times L, excuse me, Q over L, and then we'd have this 1 over 2 pi epsilon naught, and so I'm sorry about that. Let's go back to the fact that we're going to substitute this down here, and we're going to say Q over 2 pi epsilon naught L, and then that's going to be the log of B over A. The Q's cancel, I think, because that's in the denominator. The 2 pi epsilon naught should come to the top, 2 pi epsilon naught L, and then on the bottom is going to be the log of B over A. So I think that's the equation that you end up with. Probably seen that. We may have derived that in class once before for a cylindrical capacitor. That should be the capacitance. Had a feeling that might take a while to derive, but that's where we're at. If you have a partially filled capacitor, there's a lot of sequence here. This is the partially filled capacitor, the last problem. We're going to move past the idea of a cylindrical capacitor and just looked at this partially filled one. You have a third of the space filled with some value with a dielectric constant 2.75, and the other is part A. It has just air in it. It says initially this space is just filled with air, so forget about the capacitance, the dielectric part, that'll come in part B. But we're looking at these having a separation distance of D, square plates, sides of 5 centimeters, and a separation of 12.5 centimeters. And the first thing they want you to do is just calculate the capacitance. So we can go back and do exactly what we did at the beginning of this video. Put in our numbers, 8.85 times 10 to the negative 12th. For the sake of time, I'm just going to leave out the units. This is going to be 0.05 meters times 0.05 meters because their sides are a square having the same sides, and then we're going to divide by 12.5 centimeters, which is 0.125 meters. And that's going to give us the capacitance. Without the capacitor being filled with a dielectric, we're going to get 1.77 times 10 to the negative 13th farads. The last step would be to see what would happen if you have this partially filled. How is that value going to change? So it says here, with the region filled 1/3 with a dielectric constant of 2.75, what's the new capacitance? So what we're going to do is look at the fact that the new capacitance should have 1/3 of some new value plus 2/3 of whatever the old capacitance would be. So I'm going to take 1/3 of kappa times whatever it was before, the old capacitance, plus just 2/3 of what it was before. Okay, so then we can just calculate out 1/3, and then this is 2.75 times the number 1.77 times 10 to the negative 13. And then the last step would be 2/3 of that same number. And I'll quickly write that down, 1.77 times 10 to the negative 13. If you do that, that will give us the new capacitance. So I'm just going to write that down as an answer of 2.80 times 10 to the negative 13 farads. So by adding 1/3 of a filled capacitor, we have grown from 1.77 to 2.8 times 10 to the negative 13. I hope that was useful. I believe that's the answers to all of our questions. So that's the end of E&M number 10 check-in. Hope you have a great one. Stay safe. Thanks.